In this video, we're going to talk about the difference between strong acids and weak acids and how that will affect the pH of a solution. So in chemistry, the word strong has a very important definition, and it means 100% reaction. So a strong electrolyte breaks up 100% in solution, and a strong acid will react 100% with water. So let's look at nitric acid, a good example of a strong acid. When it reacts with water, it does so 100% to make hydronium ion and nitrate counterion. Now, when I say 100%, there's no reaction that could actually go completely to 100%, but we mean so close to 100% that there's no measurable difference between 100% and what we actually have. So let's look at an example of this. If we were to start with an initial concentration of nitric acid of 2 molar and no hydronium and no nitrate, we would consume all 2 molar and form 2 molar of both of these. And when we're done with this reaction at equilibrium, we would have 0 molar of nitric acid, 2 moles per liter of hydronium, and 2 moles per liter of nitrate. As I said, this is not actually 0. It's very immeasurably close to 0. And the whole point is that within the significant figures of what we started with, it is 0. Nitrate's a counterion. It's not really useful for us, but if we want to look at the pH of the solution, we need the hydronium ion concentration. So take the negative log of the hydronium ion concentration to get negative log 2, which is negative 0.3. Now don't adjust your screens. If that negative sign is bothering you, there's another video on the pH scale, or the myth of the pH scale, where we address the fact that here we have negative pHs, and that's perfectly reasonable. If we were to draw a little cartoon of this beaker, which I think is a very useful thing, the idea here is, let's say we have 1 liter of this solution. What should we expect to see in here? We would find no nitric acid. We would find 2 moles of hydronium, and we would find 2 moles of nitrate, and that would be just about it. There's also a tiny amount of hydroxide, but since we're talking about our acid, the amount of hydroxide really isn't that important. So let's look at something that's weak. And in chemistry, we're going to define weak as being not strong, which sounds pretty obvious, but what that means is that it doesn't react 100%. It does react, but it doesn't react 100%. Let's look at a good example of this: acetic acid. So if we have our acetic acid and it reacts with water, and the equilibrium that happens is we get acetate ion, our conjugate base, and again some hydronium ion. And the idea here is, if I again started with 2 moles per liter of acetic acid, I would not get 2 moles per liter of hydronium and 2 moles per liter of acetate. In fact, because I've done this, I would get 6 times 10 to the minus 3 moles per liter for each of these if I were to start with 2 molar acetic acid, which is a really small amount. Now, it's not nothing, because the normal amount of hydronium in a 25 degrees Celsius solution is 10 to the minus 7 molar. So this is a lot more than we started with. So this is going to be acidic, but not nearly as much as the HCl that we looked at before, the nitric acid that we looked at before. So let's talk about this for a second. What is the pH of this solution? So if we look at this solution, negative log of 6 times 10 to the minus 3, we get a pH of 2.2. And now what would be present in my 1 liter of this solution? Well, again, 1 liter times 2 moles per liter of the acetic acid, I still would have 2 moles of acetic acid. And I would have 6 times 10 to the minus 3 moles of acetate, the conjugate base, and I would have 6 times 10 to the minus 3 moles of hydronium. Now notice, unlike the previous case of nitric acid, here we both have the acid and its conjugate base present. And that's the hallmark of a weak acid, because a weak acid will not react 100%. Notice though, acetic acid is really weak, meaning that the amount of acid that we started with is pretty much unchanged. What makes it so weak? Well, it's the equilibrium constant associated with this acid. So let's see, I'm going to abbreviate acetic acid as HAC, just so that we can do this a little bit more quickly. And we get acetate and hydronium. So we know that we started with 2 moles per liter of this stuff. We had none of this. And we had around 10 to the minus 7 moles per liter of hydronium if we were talking about 25 Celsius water. We know that we're going to consume some of our acid, we're going to form some conjugate base and form some more hydronium, and at equilibrium we're going to have the 2 molar minus x of the acid, x moles per liter of the acetate, and 10 to the minus 7 moles per liter plus x of the hydronium. Now, we already know what x is because we measured it. It was 6 times 10 to the minus 3 molar. So notice that this x over here is kind of small compared to the 2 molar. I'm going to ignore it for now. And same thing over here, that this x is much larger than 10 to the minus 7, so I'm going to ignore it. Let's put it all together. We know that Ka, which is the acid equilibrium constant for this equilibrium, is just the activity of acetate times the activity of hydronium over the activity of the acetic acid. Remember, the activity of water is 1. And if we plug in all of these numbers, which is 6 times 10 to the minus 3 squared over 2 molar, I get 1.8 times 10 to the minus 5. As far as equilibrium constants go, it's relatively small. Relatively small means that we're going to tend to have a lot of reactants at equilibrium, and we're going to tend to have very few products, and that's Ka. The larger Ka is, the more products form. The smaller Kas, the fewer products form. The last thing that we should talk about is, just to make sure that we're clear, is that strong does not mean the same thing as concentrated. And so let's look at one of these situations. If I have a solution that's pH equals 2, we might ask ourselves, is this a strong acid or is it a weak acid? And the answer is, we don't know. Well, it could be 10 to the minus 2 molar hydrochloric acid, because in 10 to the minus 2 molar hydrochloric acid, I'm going to have 10 to the minus 2 molar hydronium, which means I'm going to have a pH of 2. Alternately, I might have 2 molar acetic acid. That's the one we looked at just before. And so I don't have to prove to you that the pH is 2. 2 molar acid, 10 to the minus 2 molar acid, 0.01, right? Molar acid. Here we have 2 different acids with 2 different concentrations getting the same pH. So pH alone doesn't tell us whether an acid is strong or weak. It simply is a measure of the hydronium ion concentration. So this is a little bit of a review of the strength of acids and bases. Hope you found it useful.